This code word here is 0, 0. I'll read it from here to here. This code word here is 0, 1, 1. 0, 1, 1. And this is 0, 1, 0, 1. And this is 0, 1, 0, 0. So I've taken the tree and shaken it. And these are the code words here. And the statement is that these are the optimal code word lengths for this probability distribution. Here we'd have to normalize by 12 over 21 for, but that won't change the algorithm at all. Okay, here's another example. Do I have a better example? No. Six, 7, 3, 9. Okay, here we go. This goes to 8, and the 7 and the 6 come down here, 9 here. 7 and 6, 13 up to here, 9 and 8. Ooh, excuse me, 9 there, and 8 here. And now this is 17, 13, 30. This will give you the code words here, and they're more interesting. See, this is basically a unary code. 1, 2, 3, and then you break the tie at 4. That's because the probabilities fell off too fast. If they didn't fall off at all, you'd get pretty much all equal length code words. Here, let's see, what do you get? Here you get a code word of length 2, 1, 1. You get 1, 1 for this one, and so on. Okay? That's a more interesting set of probabilities because we actually had these going surging high into the list and then being ignored for a while. The proof of the optimality of Huffman coding is essentially this. The optimality of a code for 1713 is obvious, but you can show that by expanding this code word, by adding a 1 and a 0 to it, you get an optimal code for these 3 probabilities. So basically, you take this probability distribution and do what's called a Huffman reduction to get this, 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 and this. Then you find the optimal code for this by inspection, 0 and 1. And by augmenting it with 1 and 0 for the expanded node, you get an optimal code at each stage as you go out, and you're done. By the way, this is optimal for 20 questions. Here are some objects, 5 of them. Here are their probabilities, and I want you to determine which object it is. So my first question should be, is it the first object? If it isn't, my next question is it the second object? You see why this is a boring example. It's a unary group. The third question is, if you get no, is it the third object? If you get a yes, fine. If you get a no, then you say, is it the fourth object? By the way, now you can stop. Because even though you haven't asked whether it's the fifth object, you have determined that it's the fifth object. So this minimizes the expected number of questions you need to determine the missing object. Now, in 20 questions, maybe all 2 to the 20th objects are equally probable, in which case the Huffman coding procedure would say that you must ask all sequencers of 20 questions. Now you can ask them in a batch or you can ask them sequentially, again, just like as in gambling. The batch would be, is it in this collection of sequences? You get a yes, and now you keep narrowing it down. You cut it in half each time. And 2 to the minus 20th times 2 to the 20th is 1. Here's a challenge for you. What if you asked questions at random? What's a random question? Well, I would pick the indicator function for the set at random. I'd flip a coin. I call this heads, tails, heads, 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 let's say, by flipping coins. And then I'd say, here's the object in the heads category, or the tails. So all subsets are equally probable. I might even, my random question might even be stupid. If I got all heads here, I'd say, is the object one of these? Well, you already knew that. If you ask random questions, you might ask, what's the expected number of answers you need before you can identify the object? Remember, if you ask smart questions, 20 questions will suffice to identify 20 objects, 2 to the 20 objects. If you ask random questions, there's a sort of a nice answer. 23 questions. That's 3 more than the 20. Will give you a probability of error of at most 2 to the minus 3. 1/8. So if you ask, say, 7 extra questions, your probability of error is, why did I do that? 1 over 128 at most. So random questions aren't bad, because the entropy, remember, might be 20 bits, and 3 or 7 are small compared to 20. So and this is the sort of thing that comes up with channel capacity. If you do things at random, it's not much worse than doing them the best way possible, at least in the right context. So we have 22 questions is an application of this. And group testing is another. In World War II, they needed to know which people participating in the Army had certain diseases. And these diseases were sort of rare, like maybe 1 in 40 people would have it. And so they could test each person individually. There are 1 million people in the Army, and that's one way to do it. But another way to do it is to gather the blood samples 20 at a time. And now a sample will be good. You can then say all of these are good, or it will be bad, and then you can hone in on who has the blood that's associated with the disease. So it turns out that's exactly what the 20 questions problem is all about. Here are the probabilities. Each of the individuals has the disease. And now what you're doing is, with your first question, you are choosing one set of individuals against another, and you're testing them to see yes or no. You know, you're trying to isolate the people with the disease. And I guess here there would be only one person with defective blood, and you would then be isolating him by testing in groups. So there's a problem on the homework called bad wine, on which instead of having to test the bottles one by one, that's the unary code, you would pour the wine in batches and taste it, and if this was good, then you know the bad wine is in the other, and you could do it. And 20 questions is optimal for that. All right, now, what about D-area codes? What if you got a yes, no, or a maybe? In other words, so let's look at Huffman coding.